Hello everybody, how's it going today? My name is Connor, welcome back to another video. Today we're going to be once again talking about my game engine by running Rust called Weaver. It is coming along quite a long way since last time I updated you guys on it, so I wanted to kind of very quickly go over everything that's changed. I know it's been a while since I've uploaded again, sorry about that, you know me by now. So, where we left off with this was we were talking about how I was kind of modularizing and generalizing the whole code base. Um, via the use of plugins. And what I ended up doing was I ended up writing a lot more plugins for the code, um, and just kind of adding functionality into the game engine as I went, so adding it kind of in that modular kind of way. And then we also talked about my new render architecture that I'm using for this. Really, a lot has changed, but we mainly I want to skip over most of what's changed because it's all been mostly back-end stuff. I will go over eventually, and also a lot of it is subject to change as well still, so I don't want to make a video about my project and how much I've worked on it and then change all that like within the next video like I normally do. Trying to stop doing that. So uh, yeah, so what we have before us here is we have this little scene, and the keen-eyed amongst you and the people in the know amongst you, I recognize this as part of a map from a nice little video game called Quake 3 Arena. This is actually Q3DM6 that we can actually fly through here. And as you can see, some of the textures are a little messed up, some of the shaders are a little messed up. But you see we got that nice little skull model up there. We got this we got the big open, quad damage area where the quad damage spawns, and the big uh, jump pad up to where the rocket launcher spawns right around here. So, um, and as you can see, it's running fairly smoothly. I've done a lot of work on optimizing this part of the renderer that renders these maps. So, you see it's running about 500 to 1,000 FPS, approximately, depending on what part of the map we're in and what we're doing at the time. Um, so, why did I do this? Why did I write a Quake 3 map loader and renderer? And the reason why I wanted to do that was just to kind of put Weaver through its paces a little bit and kind of test the flexibility and robustness of its existing APIs. So, in particular, I wanted to put the renderer through its paces a lot. New rendering API that I created that I kind of talked about a little bit last video. It's gone through much more iteration since then, but it's going to go through much more iteration after I finish recording this, because that's my next task I want to do. Is I want to really robustify the renderer a lot more and make the API a lot cleaner. So, yeah, I learned a lot by writing this Quake 3 map loader, and I got some ideas on what I want to change next. So, there's one idea in particular that I wanted to implement it first, because I figured it would be a nice little introduction back into the game engine's code for me to work on it some more. And what that idea that I had of what to work on next was the asset loading pipeline. So obviously, I'm writing a Quake 3 map loader. I'm going to have a pretty robust pipeline for loading these assets and loading all these textures and shaders and models into the game engine and into the ECS world. So how did I go about doing that originally? Well, I can actually pull up an old commit of Weaver on GitHub here. I'm going to make this full screen for you guys. I should probably write a README for Weaver at one of these points, right? Anyway, going into crates, going to Weaver asset. Maybe it's a bit bigger for you guys as well. Going to crates, going to Weaver assets. You can go into the source, and then we can kind of go over how this worked originally. Let me get this a bit more bigger for you guys. Kind of go over how this worked originally, and then later we can go over what I changed and how I made it better. So, first things first, as you see, we're defining this ID, which is asset ID, which is literally just a single U64 unsigned 64-bit integer identifier for a particular asset in the ECS world, kind of similar to an entity ID. Then we have the asset trait, and what the asset trait is just a marker trait for anything that can be an asset, and also it implements downcast sync. And then we get into handle. A handle is basically it just contains a asset ID for a specific asset and is also generic over the type of asset that's handled too, which allows for more type safety things thanks to Rust's type safety features. And then I can create an invalid handle and blah 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 from a UUID. Then we have all the handle stuff, Then we have this assets struct. It's assets resource actually. This is an ECS resource, so it's globally available throughout the entire game engine, throughout a single world at least. What this asset struct is it's just a storage that maps the asset IDs to the particular type of asset that this asset storage is for. So you see this is also generic over the assets, the asset type that it is storage for. Insert the assets into the storage. We can also insert it and not just have it generate a new ID for us, and we can retrieve the assets from the storage. So pretty typical stuff. Then we have some helper traits for adding assets and asset loaders to that app. And speaking of asset loaders, let's go into loading, which is where a lot of the stuff that I really wanted to rewrite was contained. So first things first, I have this loadable trait, which is literally just like a sub trait of asset. Sub trait of asset. And then we have the file system struct, and this is actually mostly unchanged between the two versions of this API. What the file system is just a virtual file system. Allows creation of a virtual file system for from multiple root directories and archives. So like say you have like a bunch of like different directories that all contain your game data. Well, you can kind of consolidate them into one virtual file system, quote unquote, using this this abstraction, and it'll act as if they'll all be merged together, right? So, and you also include zip archives in that. So you can see we have zip archives here that read from files. So pretty cool. We can just like also in the event of collisions, event of conflicts, and like say there's like a file that's in both directories that are named the same thing in the same path in multiple different roots of the file system, then it'll just prefer whichever one was added first. So pretty cool. Allows you to read from the archives and the path in the file system. So then we have the loader trait, and the loader trait is responsible for implementing the logic for loading an asset from the load context, which I'll get into in a sec. Load context basically just contains a file system and an original path that you're trying to load from. But I'll get into that more in a little bit. And then we have the asset loader system parameter, which contains a reference to mutable reference to a loader for a particular type of asset, mutable reference to the world, and a bunch of other stuff that's just kind of blah. This actually would appear in the systems. Like, say you had like a system that was like taking say you had like a system running on init that needed to load an asset from the disk. Then you would put in your system's parameters. You would put the asset loader for this particular type of asset and this particular type of loader that is going to load this asset. And then the load context. And the load context is where things get kind of messy. So let's go up to that. You see this load context. This is why I really didn't like what I was doing here. The idea here was to have semi-limited world access while inside the loader implementations. Basically, while you were inside the loading logic for this particular type of asset, you would have kind of limited access to the world, to the ECS world, and from that you'll be able to load retrieve other asset loaders from the world and be able to use them to load further assets in case you had like a BSP map that needed to have textures and models loaded as well. Then you could just access those resources directly from the world. You see this like get resource here. That would allow you to access these other asset loaders from the world. But here's the thing, is like I ended up in a situation where I needed to just manually drop these resources because I needed to make sure that I wasn't accessing the resources twice at the same time, because that leads to pointer aliasing, borrow aliasing, all kinds of undefined behavior stuff that you really don't want due to the way that the resources internally work inside Weaver. So that was a big old mess. I really did not like how I was doing it here. It required lots of unsafe code and just lots of messy stuff, and I really didn't like how I was doing it. Plus, if I was going to do it in such a way that was requiring other asset loaders to load another type of asset, then I could just use a system for that, you know? And systems already have this dependency graph and multiple mutable aliasing kind of prevention mechanisms in them that allow me to safely use multiple asset loaders at the same time instead of having to do this whole manually drop type crap that I ended up having to do with the load context. So that was just a big old mess. I decided to scrap this idea entirely. So let's talk about some of the problems that this method has. So with the load context, with the inline calling the other asset loaders just to load things immediately as I need them. For one, this method to see the load thing here, it only allowed loading from a path from a file system, and so no other sources of loads, no other sources of like assets, like say like a network path or like raw in memory bytes or like something like that. You couldn't do that with this system. There was no way to extend it to make it so you could do that. So that was kind of a limitation. For two, another problem with this method is that the asset loaders needed to call each other directly, which kind of led to them recursively bothering each other from the world and causing all kinds of dependency issues. So that was a big headache. Like we already kind of touched on that a little bit. And then also assets that depended on other assets, asset loaders that depended on other asset loaders, who have no way to indicate what other kind of assets they needed ahead of time. And they would just kind of be loaded immediately as if they as they were needed, which we already kind of talked on that. So that's enough of that. Let's get into what my new and improved asset loader API can do. So let's go back to Visual Studio Code here. So this is a new API. That was the old API. This is a new API. So let's go into the same file, the Weaver asset lib.rs. We still have the asset IDs, kept that. Still have the assets, kept that. Still have the handles, kept that. Mostly the same. Assets work exactly the same. Asset storage works exactly the same. File system, I kept that as well. That works exactly the same. It's just copy and pasted basically. Get into path and file system in a sec. See, now we have this trait called load source. And I really should document all this so I could actually read off of that. But anyway, I have my notes over here. The load source trait is one of the distinguishing generic type parameters for a loader now. So you see before, loaders, where's loader? Loader. It would take a type parameter for a loadable. And this would just be the asset that it was trying to load. Now what we have is, if we look at loader now, we have two type parameters. One is a asset that's trying to load, same as before, and the next one is the load source that we're trying to load the asset from. So this is just a trait. This is literally just a marker trait, really, for anything that can be used as a type parameter in a loader to distinguish it from loading from different types of sources. So you can see I already have a few implementations of load source here, just for built-in stuff, like for path buff. I can load from a path, basically, from a file system. I can load from a path and a file system, which is where this comes in, because it allows me to not have to rely on global file system throughout the entire game engine. I can just pass in a pointer to the file system that I want to load from, and then the path I want to load from the file system, and then I can just have it all be self-contained. So I even added a from implementation for a tuple of path and file system to just make a new path and file system from that. So, and that allows me to do some cool stuff like allowing me to directly load anything that can be converted into a path and file system. So it was just such as that tuple that you saw earlier. So we now have the and also the appropriate load source here is actually passed into the loader's load function. So you see the source is S, that's the load source that we're getting. You also see we have another parameter here in the load function called asset load queues. So that's the main distinguishing difference between my old implementation and my new implementation. So the new implementation allows me to, instead of immediately, see like I have I'll use BSP map example again. say I have this BSP map that I want to load the textures for. So I'm in the BSP map loader, and suddenly I need to load texture, right? So before, what I would do is I would just immediately load the texture in line. I would retrieve the texture loader from the world as a resource, and I would just load the texture right there and then. Now what I'm doing is I'm actually deferring all the loading to the same time. So I'm doing that by using a load queue. So as you can see, we have this asset load queue structure here. This is a resource. This is a resource in the world that is kind of analogous to the asset loader. Yeah, now kind of analogous to the asset loader from the old implementation, where you load things through this, right? So you load, you call load or you call enqueue or whatever on this to load your thing, or at least to enqueue the load of your thing, just to queue up and schedule the load of your thing that you're trying to load. So, sorry, that was my phone a minute ago. So you have these asset load queues, and you can enqueue a load of something that can be converted into a load source. Again, the load queue is generic over the asset that's loading, the loader that's loading the asset, and the source that it's being loaded from. So it's a very highly generic, highly modular API here, which is both a good thing and a bad thing. It's kind of a pain to write it all out, but it is highly customizable, which is nice. So it's all using a bunch of traits and trait bounds and stuff like that. It's great. So see, I can enqueue a load of something that can be converted into a load source, and that will immediately return a handle to that asset that is going to be loaded in the future. So before I had this concept where every time I had a handle to an asset, it was an asset that was already loaded into memory and just loaded into the storage. Now that's not quite the case anymore. A handle can point to an asset that doesn't actually exist yet. So that's something I gotta keep in mind as I'm working with this new API. But it's a trade-off I'm willing to make because it allows me to defer all the actual asset loading and loading into storage until a later time. So I can actually just get the handle right away, and just I push this asset load request to the DIL queue. And what this asset load request does is it's just it's a holder for the handle that I'm going to assign to eventually, and the source I'm loading from. So that's about it for that. So I have the load sources, I have the asset load queues, and now I have the magic that kind of brings this all together is I have the load all assets system. So remember I mentioned before where I wanted to have all of this kind of work together as part of a system, or I wanted us all to work via systems, where I wanted it to have this kind of automatic dependency management, automatic resource management that was already happening for systems. So I did that by converting all the loading logic into an actual system. So see, we have a mutable reference to the world here. The system cannot run at the same time as any other system, but they will run in sequence with each other for every type of asset, every type of loader, and every type of load source, right? So we have we retrieve the load queue from the world, we retrieve the asset storage from the world, and then a couple of other things like load events and load status. This is integrated with the Weaver event API to notify when an asset has been loaded. And then we basically just drain the queue, drain the load queue. And then as of recently, I just today I implemented this multi-threaded part of it where I will load all of the assets for this particular type of asset, particular type of loader, and particular type of source all at the same time. So that's pretty cool. And what this allows me to do is allows me to use the existing system dependency graph API to basically allow for asset load dependencies, so allow assets to be loaded in a certain kind of order, right? So say I need to load my textures before I load my models, right? I can now indicate that in my asset API. So that's pretty cool. And this asset load all assets system will run every frame, and it'll just look for if the queue has stuff in it. If it doesn't have stuff in it, it immediately returns. But if it does, then it'll drain that queue, load all the assets into memory, and do what it needs to do. So, all right, we're running short on time here, so I'm going to wrap this up. But basically, what this new API allows me to do that I couldn't do before is essentially just I can now specify multiple types of load sources. Let's go over some examples of how this API is being used now. So in my Quake 3 map loader, let's go into where is it? Loader. Here we go. So you see how this new API is being used. So in the BSP loader, BSP loader. Here we go. So it's a resource. It can be created from the world. because it has default implementation. And then I can import loader for BSP and path and file system. So this is the asset I'm loading again, and this is the thing I'm loading it from for BSP loader. And it's to do, but I can now use this path and file system to read the bytes from the file system and then parse it as I want. And oh yeah, I forgot to mention this load queues thing, asset load queues. So all this does is this just allows me to quickly retrieve the asset load queue for a particular type of asset and queue it up for a load. So this is a thing that's passed into every load function. So we got the asset load queues here. We got the load source, and that's all we need to enqueue a load on this thing. So this is where things are actually being read from a file system. It's right here in source.read, right? So it's std.fs read, right? So, and then we just kind of build out the BSP tree and do BSP loading stuff. And if you're not familiar with BSPs or binary space partitions, that is just a certain way of partitioning geometry in a 3D environment. You can look it up. But now I can just load. Whenever I want to queue up something for loading, like a mesh, I can just enqueue it from the load queues, and I immediately get this handle to the mesh. So that's pretty cool. And then once I actually am done loading up all these meshes and loading all these textures and shaders and stuff, I can go in here and this function is run on every update, and it'll drain that queue and actually load everything, right? So that's dependent on at least. Whew. All right. So that'll about do it for this video. I don't really know where I'm going to go next with this. I might end up working on the renderer, like I said earlier. Might not. We'll see. But for now, thank you all very much for watching, and I will see you next time. Peace out.